This video lecture on the light sensor circuit accompanies learning IoT with Python and Raspberry Pi. If there's no light hitting the photoresistor, the code will print out the value of tau and dark. If light does hit the photoresistor, the code will now print out light. If we again block the photoresistor, we'll see dark printed out. In order to create the light detector circuit, you'll need a photoresistor, a 1 microfarad capacitor, and 3 female-male jumper wires. One lead of the photoresistor should be inserted into the socket J23 on your half breadboard. The other lead should be inserted into J26. Your 1 microfarad capacitor is polarized. The long lead, the anode, should be inserted into the F26 socket. The short lead, the cathode, should be inserted into the F30 socket. One end of the female-male jumper wire should be inserted into H23. The other end should be connected to GPIO4. That's a general-purpose input-output pin. Your second female-male jumper wire should be connected to H26 and the other end to GPIO26. Connect one end of your third female-male jumper wire to H30 and the other end to ground on the Raspberry Pi. This is a completed circuit. Double check that the capacitor leads are inserted into the correct sockets for the anode, the positive, and the cathode, the negative leads. I used a red jumper wire to connect to GPIO4, a green jumper wire to connect to GPIO26, and a gray jumper wire to connect to ground. You'll connect the red jumper wire to GPIO4 on the Raspberry Pi, the green jumper wire to GPIO26, and the gray jumper wire to a ground pin. The voltage across the capacitor is equal to V0 times 1 minus e raised to the negative t divided by RC. The voltage from GPIO04 when it's turned on is V0, and that's 3.3 volts. The voltage across the capacitor, VC, is 0 when time is 0. As time goes to infinity, the voltage across the capacitor, VC, goes to 3.3 volts. The time t that it takes for the voltage across the capacitor, VC, to go to 3.3 volts is based on the value of the time constant, tau, and tau is equal to R times C. The resistance, R, times the capacitance, C. When the light is on the photoresistor, the resistance is lower. Thus, the time that it takes for the voltage VC to go to 3.3 volts is less. When there is no light on the photoresistor, the resistance is higher. Thus, the time that it takes the voltage VC to go to 3.3 volts is greater. Once the capacitor is fully charged, current will no longer go through the capacitor to ground. The current will go to GPIO26. You can determine the amount of time it takes to charge a capacitor based on when the voltage goes high on GPIO26. Let's look at the code. From the GPIO0 package, we'll import the digital output device and the digital input device classes. From time, we'll import sleep and time. We're going to create two functions, a main function and a getTimeConstant function. In our main function, we'll define which pin will be the charging pin and which pin will be the measuring pin. Our charge pin is on GPIO4, our measure pin is on GPIO26. We want to charge a capacitor, so we'll create a digital output device associated with GPIO4. We'll want to determine when the voltage goes high on GPIO26, the measure pin. So we'll create a digital input device. The getTimeConstant function has two parameters, charge and measure. We'll turn on the charge, and then we'll access the current time. And this is the number of seconds since the epoch, and store that into the start time. While the voltage is not high on the measure pin, that's when measure.value is equal to false, and our time that we've waited is less than or equal to 2, we're going to sleep for 0.0001 seconds. Once the voltage goes high, we're going to access the time once again, store that in the end time. That will be used to calculate the approximate value of tau, the time constant. That'll be the end time minus the start time. We'll turn off the voltage to the charge pin and return the value of tau. We'll set the value of the capacitance to be 1e minus 0.6, that's 1 microfarad, and we'll sleep for just a couple of seconds to allow our circuit to stabilize. Let's add a try block with an infinite loop while true. We'll call the get time constant function, pass in charge and measure as arguments, and store the return value into time constant. Then we'll print out the time constant. If our time constant is less than or equal to 0.002, we'll print light, otherwise we'll print dark. We'll sleep for 0.1 seconds at each iteration of the while loop. We'll add an except block for if the user presses Control-C to gracefully exit out of this infinite loop. We'll print exiting, then we'll call the close method on our digital output device object, charge, and call the close method on our digital input device object measure. Now to exit out of this code, you'll press Control-C. After pressing Control-C, you can disconnect the wires to the Raspberry Pi. Disconnect the gray wire that's connected to ground, disconnect the green wire that's connected to GPIO 26, and then disconnect the red wire that's connected to GPIO 4. For more information on learning IoT with Python and Raspberry Pi, visit www.learningiot.net.